Okay. No, I don't want to minimize that. Share screen. Okay. Okay, so again, just to recap, force is, weight is a force due to gravity. W equals mg, mass measure of inertia, units per kilograms. It's to be a constant because you're not going to create or destroy mass. And remember, weight, it depends on local acceleration due to gravity, depending on if you're in different planets or stuff like that. Now, every particle, or if you use the word object, doesn't really matter, in the universe experiences a force on every other. So, for example, there is kind of a force that's going on between myself and the center of the Earth, or maybe myself and the table next to me. It might be a very small force, but it's nonetheless a force. There's an equation that's used to calculate that. G is a constant. It's a really wacky number, a lot of wacky units, but the units actually make sense. M1 and M2 are the masses of the two objects that you're considering. R is going to be the distance between the two objects. Between the centers of the two objects. And if you think about the units, they do make sense, because if G is a Newton times meter squared over kilogram squared, and you have two masses, you have a kilogram and a kilogram, and you have meters for the radius squared. R stands for radius, by the way, but we'll just call it distance. Then, of course, these cancel, and these go up canceling. Then you just newtons at the end. So you have to find the gravitational attraction. So there's a 75 kilogram boy, a 50 kilogram girl. They're staying 1 meter away from each other. There's still a gravitational force between them. It's very, very small. But you would just do this: 6.673 times 10 to the negative 11 power over 1 meter, so 1 squared, times 75 times 50. Excuse me. Then what you want to do is just use a calculator, which actually I foolishly left mine in the other room. I'm a little too lazy to get it. So let's see here. I think I have scientific notation. 6.673 times 10 raised to the negative 11 times 75 times 60. So it's a pretty small number. Let me actually kind of did it wrong. 6.673 times 10 raised to negative 11 power. Okay, just round it too soon, whatever. Times 75 times 50. Yeah, I'm up getting 3, 4, 5, 6, 7. So 2.5 times 10 negative 7 newtons. So again, very, very small. I mean, but there is some sort of traction. That's just one of the laws we have to accept. Finite acceleration due to gravity. Since weight is the force, of gravity, then you could actually calculate it. So for example, the force due to gravity It's the attraction between the object and the Earth. So you could be an object. The chair next to you could be an object. So m will be the mass of the object. Come on. me could be the mass of the Earth. And re is distance between the object and the Earth's center. So yeah, so if you actually, and so you can see that when you set weight due to or force due to gravity, so weight, when you set it equal to this equation here, those are going to cancel, leaving you with this. So if you actually were to go through that computation, let me actually clear some stuff here. Okay. Come on. So you got 6.673 times the mass of the Earth, which actually I don't know, so I have to look it up. The radius of the Earth, I don't know either. I also have to look that up. So let's do that right now. Mass of Earth. Okay, 5.972 times 10 to the 24. Radius of Earth. So 3,950. So there was the kilometers. So because of kilometers, I'll change that to meters. So you have to do 6,378,000 meters squared. So why don't you guys go and calculate that on your own? And tell me what you get. So we took the constant, which is just accept it for what it is. It's called the gravitational constant. The mass of the Earth and the radius of the Earth, but radius of the Earth squared. And notice I was careful with my units, make sure I did the units all correctly. This is going to get us g, little g, the acceleration due to gravity. You guys should get 9.8. I'm going to do it on my cell phone here, which, again, it's not smart to use a graphing calculator. So let's see here. 6.673 times 10 to negative 11. Darn. Come on. Times 10 raised negative 11 times 5.972. Come on, man. 5.972 times 10 raised to 24 power divided by parentheses 6378000 squared. And you should get 9.806 or 9.807. So that's where it comes from, by the way. It comes from that. So it's not just some number that someone arbitrarily came up with. If you actually take the Earth, and how that's found, I don't know. The radius of the Earth, I think you could probably find ways to measure that. The gravitational constant, I don't know where Newton came up. Sir Isaac Newton came up with that, but you can see this. It helps us determine, figure out where that actual 9.8 came from that. So kind of cool little derivation. Any questions so far? All right. So we're going to do some examples, but just one thing we have to talk about a strategy for doing these kind of problems. So let's talk about our strategy here. So usually, hold on a sec. Hold on. I'm not sure what's meant by the first bullet point. Give me one sec here. Okay, now let's draw. Got it. So you want to identify your known variables. Involved and draw a picture. You always want to draw a picture when you're doing force. Then what you want to do is list your principles, like what kind of like formulas you're using, stuff like that. And you draw something called a free body diagram. I'll show you how to do that in a little bit. You apply the formula F equals ma. And check your answer for a reasonable solution. I want to make sure it kind of makes sense. You draw only forces acting on the object, and you represent the forces with vectors as arrows. So for example, let's take a look at this. So you have like a cinder block on a table. So what's happening is that the block has weight, force due to gravity. Also, the table pushes up on the block. Take some time to copy that. That situation we have there with the table and the cinder block, this is actually using the third law of motion. For every force, there's an equal and opposite or reactive force or equal opposite reaction. So of course, if you have a block, that's going to fall. It wants to fall because it has gravity weighing it down. So it has weight, force due to gravity. But the table pushes up on it too. Now, the force, so this right here, excuse me, this right here we like to call oh great, my stylus just died on me, so I'll have to charge it. At least my mouse is going to be a little messy. This right here we call the force due to gravity. Or you can call it W. Or you can call it mg. So you can do capital F with a subscript g, or you just go with a capital W, or you can go two lowercase letters m and g. They all mean the same thing. They're all the same thing. That's just a force due to gravity. We all have it. You guys have it right now as you're sitting in your chairs, or if you're lying on your couch, or sitting on the floor, if you're lying in a hammock, or you're lying on a, I don't know, if you're sitting in your backyard, lying on the grass. We all have that. This right here, the table pushing up on you, or pushing up on the block, is called Fn. The N stands for normal. Now be careful with the word normal. It doesn't mean like, oh, things are regular, if you're feeling normal, normal behavior, what is the new normal? Normal means it's perpendicular to the surface. So the word normal usually means perpendicular. So this is clearly my surface, the table, and there's a force acting perpendicular to the table. Because that's the surface the object lies on. Yeah, sorry, this is just getting really messy. I wish my stylus was working. So it's a perpendicular component force. Okay, I'm just going to abbreviate perp. I don't feel like writing the whole thing. And it's a perpendicular component force between two objects when they touch. So a table and a block, they're touching. So it's basically a force that's perpendicular to where they're touching. They're touching on the surface of the table. So that's what you got. So weight pushes down, right? The weight from the block is pushing down. So the table pushes up. That's a long P there. That's totally third law. Normal force doesn't always equal the weight, mind you. It's just sometimes they do. But you draw a free body diagram. To help you find an equation for this. Now, let me kind of help you out with how we're going to make this equation, because that's the part that's probably the toughest, I'd say. First is the part that I struggled with when I first took physics, because I never quite understood the strategy for this, or really quite considering all the situation, all the things that are happening here. So when a problem asks for the parent weight, you obviously want to find the normal force to help you do that. Let me fix that. Okay, I think my stash might have a little more juice now. So does anyone have anything copied? Okay. So here's, yeah, I think probably because I'm using my mouse, I'm forced to go slow. So you guys can keep up. Okay. So before I do this example with the lady, yes, that's still not working. Awesome. Okay. Let's look at this situation one more time. Now, the thing that I need to emphasize is something called F net. When you hear the word net, what do you guys think of? Like, let's say net profit. What does that mean when you have a net profit?
Total.
Good. Someone saying something? So net profit. What does that mean? What does it fall finance? Okay, I'll start cold calling. Isaac, what does it mean if you have a net profit?
Oh, I said it was the total.
So, for example, if I were to create a lemonade stand and I spent $100 and I made $300, what's my net profit?
200. It's like
Sure,
the total
great.
subtracted
Yep.
from what
Yep. Exactly.
the cost.
It's what's left over. That's what net is. Now, sometimes it could be negative too, just so you know. If you're not a good business person, or if you buy like a stock in a company, you could be down also. So it's going to be, and usually we do this. We set equal to mass times acceleration. But it's also a change in your forces. I think I might buy a second stylus so I don't this situation here. But it's also a change in your forces. So let's look at the situation again here. What two forces are acting on this? Normal force, which is positive, but the weight due to gravity is working against it, so we'll say minus W. And that's going to equal your net force. So we consider normal to be positive because it's going up and weight going down, so we make that negative. So that's what happens. Now it's going to equal, or it's going to equal MA. Whoa. Here's the deal though. Is the block moving? So Sean, what do you think here? Is the block moving?
No.
So what's the acceleration going to be? It's not moving.
Yeah.
Perfect, good. So the block is not moving. Yeah, sorry, this is really slow. So the block is not moving. So you have 0, yikes, acceleration. So that means that Fn minus W equals 0. If that is true, then Fn equals W in this case. But it's not always going to be true, because what if the thing is moving? Then you have to take that into consideration instead of equal to ma, where m is the mass of your whole system. So that's why I was saying earlier that normal force doesn't always equal weight necessarily. In this case it did, but that's not always true. And that's yet another diagram just showing that the normal force is always perpendicular to the surface. Okay. But that's going to be a key thing we're going to talk about often. You have to understand is if something's not moving, get 0 force. Or if it's constant velocity, still 0 force. A lady is weighing some bananas in a grocery store when the floor collapses. If his bananas mass 2 kilograms, the floor is accelerated at negative 2.25 meters per second squared. What is the apparent weight of the bananas? Okay. So first off, the normal force is what we're trying to figure out, right? I think I was working. Okay, good. So your net force is going to be normal force minus weight. Your net force is also m times a. Normal force we want to find. Your weight is going to be mass due to gravity. Sorry, weight due to gravity, or force due to gravity. So we know the mass of all the bananas is 2. The acceleration is negative 2.25. Again, the mass here is 2. And the weight due to gravity is negative 9.8. Actually, because we already put a minus, because net force should be all the forces added up, actually. But because you already have the minus here, there's no need to make G negative, because you already have the minus there. So F net actually should be technically, I mean, I do say change, but somewhat force, just sometimes your forces are in a negative direction. So if we put a minus in front of W, you kind of already taken care of that negative for G there. And if you were to work it out, I think you'd have negative 4.5 equals Fn minus 19.6. So Fn is going to be 15.1. And that's, we would expect that to be the way the banana is before the floor fell down. So again, you're kind of just taking the information given to you. You know, F net's ma, weight due to weight is just force times gravity, and we're solving for normal force in this case. Let's look at one more, and I'll have you guys do some practice. Let's look at a ramp here. I'm gonna clear that. Okay. Ooh, yeah, these are fun ones. Okay, so a box in a ramp angle at 20 degrees. If the box weighs 50 newtons, was normal force on the box. So the weight is always going to be pointing directly down. So that's going to be mg. Now, the things that if I draw that again, so this is mg, or we call it the force due to gravity. Remember, same thing. You could say this is, or you can call it W also. So I don't really care how you express it. But for simplicity purposes, let's just call that W, the weight. Then this is going to be the weight in the y direction, and that's going to be weight in the x direction. And because this was 20 degrees right here, if you were to kind of use like some geometry principles and some parallel line kind of work, and in fact, if you were to, just trying to think the best way to kind of help you see this. I suppose if you were to draw two parallel lines, if you had something kind of like that, no, that's not really helping you guys. The bottom is that whatever angle you have here, it's going to be seen right there if you tilted, if you rotate the triangle in a particular direction. So we have 20 degrees right here. So in this case, we would say that this weight in the y direction is actually going to be your weight times cosine theta, and the weight in the x direction is going to be the weight times sine theta. So a little bit counterintuitive to what we do with projectile motion. Now, because it's not moving, so it's just kind of sitting, no motion, so there's no acceleration. Fn, so your F net is Fn minus the weight in the y direction. Because this is sitting on a ramp and it's angled, you actually have to break the weight into its horizontal and vertical components. So we're breaking the weight down into its horizontal and vertical components. And because it's motionless, your F net is 0. And Wy is going to be W times cosine theta. So W times cosine theta equals your normal force. Your weight's 50 times cosine 20 degrees, and you work that out. And if you do that correctly, you should get, I believe, 47 newtons. So I didn't want to just say, oh, here's just what you do, and just do it. I wanted to kind of show you the proper and more formal way, like using the angle, breaking it down to its components. So this red arrow here, that's the weight due to gravity. It's always acting downward. You're always heading towards the center of the earth, your weight, your force due to gravity. However, if you're at an angle, then you kind of have to break it down to horizontal and vertical components so you can do the math correctly. And this right here, this whole thing here, is called a free body diagram. You have the body, which is the object, and you're kind of freely drawing these arrows to represent where the forces are acting. So we're going to do a little bit of practice in just a bit. Kind of give you a little bit of a push here. So So let's look at maybe 4 through 7. So I'm going to clear all these drawings. Okay. So in this case, for number 4, you have 2 masses, a bowling ball and a billiard ball. You have each of their radii, and I guess they are touching each other. So what you want to do for number 4 is use this formula. Capital G and R, you have a big object and a little object. So essentially, you're going to be adding those 2 radii. Because it's the distance between the 2 centers. And the capital G, that was, we saw that earlier. So that's number 4. For number 5, you guys can figure 5 out. It's the same thing. For 6, how have you guys work 6 out? 7, the mass of the moon. So you're going to do a Google search. Sorry, that's going to be little g. My bad. Um, $11, I think I want you guys to try as well. And hold on a sec. $13 want to find. We might do 13 together near the end if you guys don't quite get to all this. For 11, and draw a diagram. I might hop in the rooms and kind of help you with 13. That might be a good idea. 11, mass 45 breaks loose from edge of a cliff. Fall straight down, magnitude there resistance that poses. Yeah, same thing. Hold on a sec here. Fall straight down. Yeah. We use yeah, I might have to hop in the rooms, help you guys 11, 13, because I know it's still kind of new to you guys. So we're gonna do 4, 5, 6, 7, 11, 13. And yeah, I'll put you guys in breakout rooms right now. So you might want to take a picture of all this. So 4, 5, using these the F equals G M1 M2 over R squared formula. 6 and 7, I kind of gave you guys a little bit of a push there. You probably want to do a Google search for number 7. 11 and 13, formulas dot diagram. I'll hop in the room and help you guys out in a few minutes. So that's what we're going to do. Let me go ahead and clear all this. We'll make new